For most of human history, the planets appeared predictable, almost obedient, tracing clean paths across the sky as if they were following rules we already understood. But one of them has been quietly refusing to cooperate, and it sits closer to us than any other world except the moon. Similar in size to Earth, formed from nearly the same material, and yet, when we finally measured its motion with precision, we discovered something that should not be there if our simplest assumptions were right. It rotates backward, and not just slightly, but in a way that forces us to ask whether the problem is really the planet or the way we think about planets at all. If you stand on the surface of Venus and watch the sky, the sun would rise in the west and set in the east, the opposite of what happens on Earth. And it would take longer than you might expect. Because one full rotation takes about 243 Earth days, slower than its own year, which means a day on Venus is longer than a year on Venus. A detail that sounds like a curiosity until you realize it violates the pattern we see across most of the solar system, where planets tend to rotate in the same direction they orbit, inheriting that motion from the disk of gas and dust that formed them billions of years ago. A disk that spun in a consistent direction and passed that spin down like a kind of cosmic memory. So when a planet breaks that pattern, it is not just an exception. It is a signal that something in its history did not follow the script. The immediate instinct is to assume something dramatic must have happened, some violent collision or catastrophic event that flipped the planet over or reversed its spin. And for a long time, that was the dominant explanation. But there is a subtle problem with that idea that becomes harder to ignore the more you think about it. Because if the answer requires a very specific, very rare event to explain a very fundamental property, then the explanation may not be as complete as it seems. It may be filling a gap in our understanding rather than truly resolving it. What makes Venus more unsettling is not just that it rotates backward, but that it does so in a way that is stable, consistent, and long-lasting, suggesting that whatever caused this state is not something temporary or chaotic, but something that the planet has settled into over billions of years. As if backward rotation is not an accident but an outcome, one of several possibilities that the system naturally allows. And that shifts the question in a quiet but important way. Because instead of asking what happened to Venus, we begin to ask what kinds of processes can produce multiple stable outcomes from similar beginnings. And why two planets that started so similarly could end up so different in something as fundamental as the direction of their spin. This is where the story stops being about a single strange planet and starts becoming about the limits of our models. Because if Venus can arrive at its current state through more than one pathway, then the rotation we observe today may not be a clear record of its past. It may be the final result of a process that erases its own history as it unfolds, leaving behind a state that looks simple but encodes something far more complicated beneath the surface. And that possibility is what makes Venus less like a solved puzzle and more like a question that has been quietly waiting for us to realize we may have been asking it the wrong way all along. The first instinct, once you accept that something is off, is to look for a single dramatic cause, something large enough to overturn an entire planet. And in planetary science, that usually means an impact, a collision, early in the history of the solar system when objects were still forming and moving through unstable orbits, striking each other with enough energy to reshape not just surfaces but entire rotational states. And this idea is not unreasonable because we already believe something like this happened to Earth when a Mars-sized body collided with it and eventually led to the formation of the Moon. So extending that logic to Venus seems natural. Perhaps Venus was struck in just the right way to flip its rotation, or at least slow it down and push it into a different regime. And for a long time, this explanation carried weight because it fits our intuition about how large changes happen in physical systems. Big effects come from big events. But as simulations became more detailed and our understanding of planetary formation improved, the simplicity of that story began to break down in subtle ways. The problem is not that an impact cannot change a planet's rotation. It absolutely can. But that producing the exact state we observe today on Venus requires a very specific set of conditions. The angle of impact, the relative velocities, the distribution of mass afterward, and the subsequent evolution all have to align within a fairly narrow range. Otherwise, you end up with a planet that spins too fast, or not slow enough, or tilted in a way that does not match what we see now. And when a model only works under finely tuned circumstances, it starts to look less like a general explanation and more like a possible story among many. One that might be true but is difficult to confirm because the evidence of such an event, if it ever existed, has largely been erased. Venus complicates this further because its surface does not preserve a deep geological record, unlike Earth or Mars, where ancient impacts leave traces that can be studied billions of years later. The surface of Venus appears to have been resurfaced by widespread volcanic activity relatively recently in geological terms, which means any scars from a primordial collision would likely be gone, buried under layers of lava and tectonic deformation. So even if a massive impact did occur, the planet itself has removed the direct evidence, leaving us with a hypothesis that cannot easily be tested against physical records. There is also a second variation of this idea, slightly less violent but still rooted in early chaos, which suggests that instead of a single collision, Venus may have experienced a merger with another protoplanet, gradually combining mass and redistributing angular momentum in a way that altered its spin. And again, this is plausible in the early solar system where multiple large bodies coexisted and interacted. But it runs into a similar limitation. The range of outcomes is extremely broad, and only a small subset leads to the slow retrograde rotation we observe today, meaning the explanation depends heavily on initial conditions that we cannot reconstruct. What begins to emerge from both of these scenarios is a pattern. They are not wrong, but they are incomplete. They explain how Venus could have ended up like this, but not why it would be likely to end up like this. And that distinction matters because in science, an explanation gains strength not just from being possible, but from being probable under realistic conditions. If you have to rely on a rare alignment of factors to explain a common physical outcome, then you may be missing a more fundamental mechanism operating in the background. This is where the reasoning starts to shift. Because instead of asking, what singular event flipped Venus, we start asking whether Venus needed to be flipped at all. Whether the backward rotation could emerge from the normal, continuous processes that act on planets over billions of years. Processes that are always present, always interacting, and capable of producing outcomes that look unusual only because we have not fully traced the path that leads to them. And once you begin to consider that possibility, the dramatic impact narrative starts to feel less like an answer and more like a placeholder. a way of explaining away a gap in understanding rather than filling it. Because if a planet can arrive at its current state through slow, cumulative forces instead of a single catastrophic event, then the real story is not about something that happened to Venus, but about something built into the system itself. Something that operates quietly, continuously, and in ways that are much harder to see without stepping back from the idea that every anomaly must have a dramatic cause. And that realization opens the door to a very different kind of explanation. One where the forces shaping Venus are not rare or exceptional, but present everywhere, acting all the time, and only revealing their full effect over spans of time that are almost impossible to visualize directly. To see that alternative clearly, you have to shift attention away from rare events and toward the forces that are always present, the ones that operate quietly over billions of years and reshape a system not through sudden shocks, but through persistent imbalance. And in the case of Venus, those forces come in three forms that are individually subtle but collectively powerful, each applying a torque that depends on the planet's state and each responding to changes in that state, creating a feedback system that evolves in ways that are not immediately intuitive. The first is the gravitational tide raised by the Sun, a consequence of the fact that gravity weakens with distance. So the side of Venus facing the Sun feels a slightly stronger pull than the far side, stretching the planet and creating a pair of small bulges aligned roughly along the Sun-Venus line. And if the planet were not rotating, those bulges would remain perfectly aligned. But real materials take time to respond, and Venus is rotating. So the bulges are dragged slightly out of alignment, one leading and one trailing relative to the direction of rotation. And that misalignment means the Sun's gravity is pulling on a shape that is not perfectly centered, producing the torque that acts against the rotation, draining angular momentum and gradually slowing the spin regardless of whether it is prograde or retrograde, always pushing toward a state where the rotation rate approaches zero. And if this were the only effect in play, Venus would likely have ended up tidally locked with one face permanently pointed toward the Sun. A stable and predictable outcome, similar to how the Moon behaves around Earth. But Venus is not a bare rock. It is wrapped in a dense, massive atmosphere. And that atmosphere introduces the second torque, one that behaves in a fundamentally different way because it is driven not just by gravity but by heating. The day side of Venus absorbs solar energy. The gas warms and expands, creating pressure differences that drive global winds. And because the atmosphere has inertia and the heating cycle is not instantaneous, the regions of maximum density and pressure are shifted away from the simple day-night line, forming a rotating pattern that lags behind the position of the Sun. And this offset mass distribution also feels the Sun's gravity, producing its own torque on the solid planet beneath. But crucially, this thermal tide does not act in the same direction as the gravitational tide. It tends to push the rotation away from synchronous locking, and under the right conditions, it can favor retrograde motion, effectively competing with the gravitational effect instead of reinforcing it. So now you have two continuous forces acting on the same system with opposing tendencies. One trying to slow the rotation towards zero, and the other capable of driving it away from that state, depending on how the atmosphere behaves. The third component is less visible but no less important. the interaction between the planet's interior layers, specifically the friction between the core and the mantle. Because Venus is not a rigid body, but a differentiated one with a dense metallic core and a rocky outer shell. And these layers do not always rotate in perfect unison. When external torques change the rotation rate of the outer layers, the core can lag behind, and the friction at the boundary transfers angular momentum between them, acting as a kind of damping mechanism that smooths out rapid changes and influences how the system responds over long timescales. Not by adding energy, but by redistributing it internally, affecting the path the rotation takes as it evolves. What matters is not any one of these torques in isolation, but the way they interact, because each depends on the current rotation rate, the structure of the atmosphere, the internal properties of the planet, and the distance from the Sun. And as the rotation changes, those dependencies shift, altering the balance of forces in a feedback loop that can move the system toward different stable states. Not a single predetermined outcome, but a landscape of possibilities. And in that landscape, the rotation rate is not just drifting randomly, but being guided towards specific attractors where the opposing torques balance out. This is the conceptual shift that makes the earlier impact explanations feel less central. Because once you have a system with multiple attractors, the final state does not require a precise initial push. It only requires that the system evolves within a certain range of conditions. And over billions of years, even small differences can determine which attractor is reached. In this framework, the slow retrograde rotation of Venus is not something that needs to be imposed from the outside. It can emerge naturally from the continuous interaction of tides and internal dynamics, especially given the unusually thick atmosphere, which amplifies the thermal tide to a level that is not seen on most other terrestrial planets. Without that atmosphere, the gravitational tide would dominate and Venus would likely settle into synchronous rotation. But with it, the balance shifts, opening pathways that include slow retrograde motion as a stable outcome. What makes this picture more challenging is that it turns a rotation into a property of a coupled system rather than a single object. You cannot treat the solid planet independently from its atmosphere because the two exchange angular momentum continuously. The atmosphere influencing the spin of the surface, and the surface influencing the circulation of the atmosphere. A feedback loop that has been running for billions of years, evolving as the sun's output changed, as the interior cooled, as the atmosphere thickened or lost components. And that long history means the present state is the result of an extended trajectory through a high-dimensional phase space, rather than the consequence of a single identifiable event. And once you accept that, the question becomes less about what flipped Venus and more about how many different evolutionary paths could lead to something that looks exactly like what we observe today. Because if multiple paths exist, then the rotation we see is not a unique signature of one history, but a common endpoint shared by several. And that possibility carries a deeper implication, that even with perfect measurements of the current state, we might still be unable to determine which path was actually taken. Because the system itself allows different paths to converge into the same present, quietly erasing the distinctions that would otherwise let us read its history directly. Once you accept that the rotation of Venus is shaped by a coupled system of competing torques, the idea of a single inevitable history begins to dissolve, and what replaces it is a landscape of possible outcomes where the system can settle into different stable states depending on how it evolves. A concept often described in dynamical systems as attractors, regions in the space of all possible configurations toward which the system naturally moves over time. And in this case, The attractors are not just different rotation speeds, but entirely different rotational identities, including prograde motion, retrograde motion, and states so slow they approach a standstill relative to the Sun. What makes this especially difficult to reason about is that these attractors can be reached through very different pathways, meaning that two planets with similar starting conditions can diverge for billions of years and then converge again into the same final state, leaving behind almost no trace of how they got there. This is not a failure of measurement, but a property of the system itself, a kind of built-in ambiguity where the present does not uniquely encode the past. In the case of Venus, simulations suggest at least two broad evolutionary routes that both lead to what we observe today, and from the outside, they are indistinguishable. In one scenario, the planet begins with a prograde rotation similar to Earth, spinning in the same direction as its orbit, and over time, the gravitational tide from the Sun steadily slows that rotation, while the atmospheric thermal tide grows in relative influence as the spin rate decreases, eventually reaching a point where the rotation crosses through zero and reverses direction, becoming retrograde, after which the thermal tide continues to push in that new direction until a balance is reached with the opposing gravitational torque, stabilizing the system at a slow backward rotation that persists over geological timescales. In this pathway, the axis of the planet remains largely upright. The change is primarily in the direction and speed of rotation, a gradual reversal driven by continuous forces rather than a sudden reorientation. In the second scenario, the story unfolds differently, even though the ending looks the same. Here, the planet's rotation axis becomes unstable under the influence of the same competing torques, drifting away from its original orientation and gradually tilting over. And as the tilt increases past 90 degrees, the planet effectively turns upside down relative to its orbit, so that what was once prograde rotation now appears retrograde from an external perspective. Not because the direction of spin has reversed in the planet's own frame, but because the orientation of the axis has flipped, producing the same observational result through a completely different internal history. Both pathways are consistent with the physics. Both can arise from plausible initial conditions, and both lead to a planet that looks exactly like the Venus we observe today, slow, retrograde, and tilted in a way that suggests something unusual happened, even though the underlying processes may have been entirely gradual. This convergence of distinct histories into a single observable state is known as observational degeneracy, and it represents one of the most profound limitations in reconstructing planetary evolution, because it means that even with perfect knowledge of the present, we cannot uniquely determine the past. The system itself has erased the distinctions that would allow us to tell one history from another. The difficulty is compounded by the fact that Venus has also erased much of its physical record. Its surface has been resurfaced by widespread volcanic activity, burying older terrain beneath layers of lava. And unlike Earth, it has no large moon whose orbital dynamics might preserve clues about its rotational history. Nor does it have a clear magnetic record in its crust that could reveal how its axis has changed over time. So we are left with the present state that is both dynamically degenerate and observationally incomplete. When you combine these two factors, the problem becomes fundamentally underdetermined. There are more possible histories than there are constraints to eliminate them. And adding more detailed models does not necessarily resolve the ambiguity, because the models themselves can produce multiple valid outcomes depending on parameter choices that are not precisely known. What this means in practice is that the rotation of Venus is not a straightforward clue to its past, but a kind of endpoint that multiple narratives can lead to. And without additional evidence, those narratives remain equally viable. This is where the earlier impact hypothesis re-enters the discussion in a different light. Not as the default explanation, but as one option among several. It is still possible that a collision or merger contributed to the current state, but it is no longer required, and it is no longer uniquely supported by the observations. It becomes one branch in a tree of possibilities rather than the trunk from which everything else grows. The deeper implication is that the question we started with may not have a single answer. Not because we have not found it yet, but because the system does not preserve the information needed to define it uniquely. And that forces a subtle shift in how we think about explanation in planetary science. Moving away from the idea that every observed feature corresponds to a specific historical event, and toward the recognition that some features are statistical outcomes of complex processes. States that are likely to occur under a range of conditions, rather than signatures of one precise cause. In that sense, the rotation of Venus is less like a fingerprint and more like a common pattern, one that tells us something about the dynamics of the system, but not necessarily about the exact sequence of events that produced it. And that distinction becomes even more important when we begin to widen the frame beyond Venus itself. Because if multiple histories can collapse into the same present on a single planet, then interactions with the broader solar system may introduce even more pathways that lead to similar outcomes, further blurring the connection between what we see now and what actually happened long ago. Once you widen the frame beyond a single planet, the rotation of Venus begins to look less like an isolated anomaly and more like a fragment of a much larger dynamical story, one that involves the early instability of the inner solar system itself. Because the system we observe today, with its cleanly spaced orbits and relatively stable configurations, is almost certainly not the system that existed in the first few 100 million years after formation. During that earlier phase, there were more bodies, more interactions, and far more opportunities for gravitational encounters that could redistribute angular momentum in ways that are difficult to reconstruct after the fact. One of the ideas that emerges from this broader perspective is the possibility that there were additional terrestrial planets that no longer exist. Bodies that formed alongside Earth, Venus, and Mars, but were later ejected from the system or destroyed through collisions. A hypothesis often referred to as a lost inner planet or Planet 5. And while there is no direct observational evidence for such an object today, dynamical simulations sometimes produce more stable, long-term outcomes when an extra body is included early on and then removed through chaotic evolution. If such a planet existed, its gravitational interactions with Venus could have altered the orientation of its rotation axis or modified its spin rate through close encounters. Not necessarily through direct impact, but through repeated perturbations that accumulate over time, effectively nudging the system into a different region of its phase space before the perturbing body disappeared. This kind of mechanism does not leave a clean signature because the source of the disturbance is no longer present, and the effects it produced may be indistinguishable from those generated by internal processes, which reinforces the idea that multiple histories can converge into the same observable state. A related line of thought considers the possibility that Venus and Earth themselves may have interacted more strongly in the past than they do now, not through collision, but through a series of close approaches during a period when their orbits were less stable, allowing for exchanges of angular momentum that could influence their respective rotations. And while current orbital configurations do not suggest such encounters, simulations of early solar system evolution sometimes show that temporary instabilities can arise before the system settles into its present form, making it conceivable that Venus experienced gravitational interactions with neighboring planets that subtly reshaped its spin without leaving an obvious trace. These scenarios are difficult to confirm because they rely on conditions that no longer exist and on parameters that are not tightly constrained. But they illustrate an important point. The rotation of a planet is not determined solely by its internal properties or its interaction with the Sun. It is also influenced by the collective dynamics of the entire system, especially during periods of instability, when small differences can be amplified into long-term divergences. This broader context is supported by models of solar system formation, such as the NICE model and the Grand Tack hypothesis, which suggest that the giant planets underwent significant migration early in their history, moving inward and then outward, and in the process, scattering smaller bodies, altering orbital resonances, and injecting chaos into the inner regions where the terrestrial planets were forming. If this picture is even partially correct, then the environment in which Venus evolved was far more dynamic than the current configuration implies, with gravitational disturbances propagating through the system and creating opportunities for resonant interactions that could capture or redirect rotational states. One particularly intriguing extension of this idea involves chaotic resonance capture, where a system evolving under multiple competing influences drifts into a configuration where certain frequencies align in simple ratios, creating a stable resonance that can trap the system even if it was not part of the initial conditions. And in the context of Venus, this could mean that its rotation rate and axial orientation became locked into a stable pattern defined by the interaction of tidal forces, atmospheric dynamics, and external perturbations, a pattern that appears unusual only because we are observing it at the end of a long and complex trajectory through phase space. The challenge with resonance-based explanations is that they are highly sensitive to initial conditions and to the precise values of physical parameters, making them difficult to test directly. But they are consistent with the broader observation that the system has multiple attractors and that transitions between them can occur in ways that are not easily predicted without detailed simulation. There are also more speculative ideas that push the boundaries of plausibility, such as the notion that Venus may have formed in a different region of the solar system and was later captured into its current orbit, bringing with it a rotational state that does not match the local pattern. But this scenario faces significant obstacles because capturing a planet into a stable orbit requires a mechanism to dissipate energy that is not readily available in most cases. And because the composition of Venus closely matches what we expect from an object formed near its present distance from the Sun, making an external origin unlikely. Even so, the existence of such hypotheses highlights the degree of uncertainty that remains when standard explanations do not fully resolve a problem. The range of considered possibilities tends to expand, not because all of them are equally likely, but because the system allows for a wide variety of outcomes under different conditions. What ties all of these ideas together is the recognition that the early solar system was not a quiet place. It was a chaotic environment in which planets were forming, migrating, interacting, and sometimes disappearing. And the properties we observe today are the result of that history, filtered through billions of years of evolution. In that sense, the rotation of Venus can be seen as a residual effect of processes that operated on scales larger than the planet itself, A record not just of local physics, but of system-wide dynamics that may no longer be directly observable. And if that is the case, then the difficulty of explaining Venus is not simply a matter of missing data about one planet, it reflects a deeper challenge in reconstructing the history of a system where many of the key actors are gone and many of the relevant interactions have left no clear trace, leaving us with a present that is consistent with multiple pasts, and a set of models that can reproduce the outcome without uniquely identifying the path that led to it. And this is where the problem stops being just about Venus and starts becoming a question about the limits of what planetary science can actually recover. Because even if we map every detail of the present state with perfect precision, the combination of erased geological history, missing dynamical records, and intrinsic degeneracy in the system means that some aspects of the past may simply no longer be encoded anywhere we can access. And that realization forces a shift from asking what happened to asking what can in principle still be known. If we list the kinds of evidence that would normally allow us to reconstruct a planet's rotational history, the absence becomes striking. There is no ancient surface preserved at global scale. No layered record stretching back billions of years like we have on Earth, where minerals and sedimentary structures retain information about past climates and orientations. On Venus, the surface appears relatively young in geological terms, shaped by widespread volcanic resurfacing that has buried or erased older features, removing the very patterns that might have recorded how sunlight once fell across the planet or how its axis was oriented relative to the Sun. There is also no large satellite orbiting Venus, nothing equivalent to the Moon that could serve as an external recorder of angular momentum exchange, because a Moon's orbit evolves in response to the rotation of its host planet and can preserve clues about how that rotation changed over time. Without such a companion, Venus exists in a kind of dynamical isolation, its past interactions not written into any surviving orbital system. The magnetic record is similarly absent or inaccessible. While Earth's crust contains magnetized minerals that align with the planet's magnetic field at the time of their formation, providing a timeline of changes in field orientation that can be linked to rotational dynamics, Venus shows no clear global magnetic field today. And whatever ancient record might have existed has likely been reset by resurfacing and thermal processes, removing another potential line of evidence. What remains is primarily the atmosphere, and even there, our knowledge is incomplete. We can measure its composition, its structure, and some aspects of its circulation. But the details that matter most for long-term evolution, such as precise isotope ratios and the mechanisms that sustain its super-rotating behavior, are still only partially understood. And those uncertainties feed directly into the models that attempt to explain how the atmosphere interacts with the solid planet to influence rotation. This is why upcoming missions are important. Not because they will provide a single decisive answer, but because they will constrain the range of possibilities by filling in some of these gaps. Missions like Da Vinci mission are designed to descend through the atmosphere and measure its composition with unprecedented precision, particularly the ratios of noble gases and isotopes that can reveal how the atmosphere has evolved over time, whether it lost large amounts of water early through rapid processes or gradually over billions of years. Information that indirectly informs our understanding of how the thermal tide may have behaved in the past. At the same time, orbital missions like Veritas mission aim to map the surface and interior in far greater detail than before, providing high-resolution topography and gravity data that can constrain the internal structure and the way the planet responds to tidal forces. parameters that are critical for modeling the long-term evolution of its rotation. Together with other planned missions, these efforts will reduce uncertainty, eliminate some scenarios, and strengthen others. But they are unlikely to collapse the problem into a single unambiguous history, because the fundamental issue is not just lack of data, but loss of information. The system has evolved in a way that allows different histories to converge into the same present, while simultaneously erasing many of the traces that would distinguish them. This has implications that extend far beyond Venus, because if we cannot fully reconstruct the history of a planet that is relatively close and accessible, then the challenge becomes even greater for the thousands of exoplanets we are now discovering around other stars. Worlds for which we often have only limited measurements of mass, radius, and orbital parameters. And yet we attempt to infer their formation histories and evolutionary pathways from that sparse data, assuming that the present state carries a clear imprint of the past. Venus suggests that this assumption is not always justified, that multiple histories can produce the same observable properties, and that without additional constraints, those histories may remain indistinguishable. In that sense, Venus is not just an outlier, but a case study in epistemic limits, showing how far we can push inference before it becomes underdetermined, and reminding us that scientific understanding is often about narrowing possibilities rather than identifying a single definitive answer. The progress made over decades of study has been real. We have moved from simple speculative ideas to detailed physical models that can reproduce the observed state under a range of conditions. We have identified the key forces, the relevant parameters, and the ways in which they interact. But the core ambiguity remains, not because the models are flawed, but because the system itself allows for multiple valid solutions. And so the question that seems straightforward at the beginning, why does Venus rotate backward, becomes something more subtle. Not a request for a single cause, but an exploration of a space of possibilities, bounded by physics and constrained by incomplete evidence. A problem that may never fully resolve into a single narrative, and that leaves us in a position that is both frustrating and informative. Knowing more than we did before, understanding the mechanisms in greater depth, yet still unable to say with certainty which path the planet actually followed. As if the history we are trying to reconstruct has been partially overwritten, leaving behind a pattern that is clear in its form but ambiguous in its origin. A pattern that invites explanation while resisting final interpretation, and quietly raises the possibility that some questions in planetary science do not end with answers so much as with a boundary, a point beyond which the available information no longer distinguishes between competing truths. And beyond that boundary, the past of Venus remains suspended, not entirely hidden, but not fully recoverable either, waiting at the edge of what we can know without quite resolving into something we can finally confirm.